this lesson, we're going to look at measures of position. So in particular, z-scores, what that means, percentiles, IQR, and outliers. So the objectives here, that you can determine and interpret a z-score, determine and interpret quartiles, interpret percentiles, and determine and interpret IQR, which stands for interquartile range. And also want to check for outliers. Okay, the z-score. Okay, the z-score will give you the number of standard deviations from the mean. Simple as that. It's a number that pops out from our formula. So for the sample standard deviation, here's our formula, and for the population, there we go. So that basically the same thing. We take x, the data point, minus the mean, and divide it by the standard deviation. If we're talking about a population, it's x minus, remember mu is the mean of a population, and x bar is the mean of a sample. Okay, similar for S is standard deviation of a sample. Little sigma is a standard deviation of a population. So let's see how this is used. Example 1. I should put a 1 there. Suppose that Bob's height is 75 inches. How many standard deviations from the mean is Bob's height if the mean height of man is 69 inches with a standard deviation of 2.8? Not sure we need that. Okay, so I meant to have this sort of fly in, but we're going to have, here is our formula. Our x is the individual point, the individual data value, 75. Again, this section's measure of position. We're trying to find sort of where individual values fall within the bigger data set. So 75, how does 75 compare? If we know a mean of 69 and a standard deviation of 2.8, what does that mean? So 75 minus the mean, so there's the mean, divided by the standard deviation of 2.9. Or sorry, 2.8. 75 minus 69 is 6. 6 divided by 2.8 is 2.14. I assume you can do those calculations without me showing you. So Bob is 2.14 standard deviations above the mean. Okay, now let's look at this on the graph where it shows up. It's best to kind of go ahead and draw out your normal curve. It would have been stated that the heights of men are normally distributed, so we draw out our normal curve, and Bob is about right there. So one natural question would be, you know, what Bob is in what percentile, or how many percent of people are shorter than Bob or are taller than Bob. So where does Bob fall sort of relative to everybody else in the data set? That's something that many people want to know. Okay, another example, example 2. A student scores 60 on a math test that has a mean of 54, standard deviation of 3, and then she scores an 80 on a history test with a mean of 75, standard deviation of 2. On which test did she perform better? When I say better, we mean relative to the class. And it's best to go ahead and draw these out on a normal curve, particularly in the beginning, to give you a better sense of what's going on. So let's do this one on the left. We'll make this the math test. And the one on the right, we will make the history test. Okay, so we have a student scored 60 on the math test, has a mean of 54. So there's our 54. Standard deviation, she's sample here, of 3. So we just have a sample, one class, we'll consider that the sample. It really won't matter the way we do these. And then a history test, she scored an 80. It had a standard deviation of 2. So let's go ahead and fill the rest of this out. So 54 with a standard deviation of 3, 57, 60, 63, and we'll go the other way, just subtracting 1 each time. 51 minus 3 would be 48, and minus 3 is 45. And similar on the history, so that's going to be 82, 84, and 86, and then we'll subtract 2 each time. 78, 76, 74. So we got a little practice on this in an earlier lesson. Okay, so where does she fall here? On the math one, she scored a 60. So a 60 is right there. So she scored 2 standard deviations above the mean. Okay, so that's something to keep in mind. On the history, she scored an 80. Oh, I messed this up, didn't I? Okay, so this should have been, she scored an 80, has a mean of 75. I bet a lot of you caught that. So 75, standard deviation of 2, so that would be 77, 79, 81. Should have given myself more room down here. 73, 71, 69. Now, where did she score? She scored an 80, which is right here. Right in the middle of 79 and 81. So this is, about 2.5 standard deviations above the mean. So she really scored better on the history exam, right? Okay, example 3. Not sure why all my numbers got left out. Human body temperatures have a mean of 98.2 degrees and a standard deviation of 0.62. Convert the temperatures below to z-scores and draw them on the normal curve. Okay, so let's look at this first one. So let's go ahead and first write down my values here. So we've got a mean of 98.2. And we've got a standard deviation of 0.62. So let's bring our calculator up. So we have 98.2 plus 0.62 is 98.82. And plus 0.62, 99.44. And then plus 0.62, 100.06. And then go the other way. So 98.2 minus 0.62. $97.58 minus 0.62, 96.96, and one more, minus 0.62. So it takes a little bit of time, but definitely worth it, 96.34. So in general, when I'm giving you homework and stuff like that, you'll have very few problems to do. But you need to make sure you do them thoroughly, right? So maybe we took an algebra class, you'd have 40 or 50 problems to do. Statistics, you're gonna have many fewer problems to do to get the full effect. So make sure that you work through these really carefully and meticulously. Okay, now we're ready for part A. So 100, kind of glance down at your curve. 100 is right around here, right? So just before, that's 100.06, so just before that 3 standard deviation from the mean. So we'd expect this when we crunch out the z-score. Remember, z is x minus, and it doesn't say here, it says it has a mean with that, so it didn't say it took a sample, so we'll assume here it's population. Again, it doesn't really matter with the formula in this one. So what are we going to have here? X, which is 100, minus 98.2 divided by 0.62. Let's crack our calculator out. We'll do 100 minus 98.2 equals, and then hit divided by 0.62. And we get 2.9. Is that shocking? No, because we drew our curve out, we expected something a little bit below 3, right? Okay, the next one, 96.96. So let's do B here. So 96.96 minus 98.2 divided by 0.62. So 96.96 minus 98.2, then divided by 0.62. So we get a -2. So 96.0, and there it is right there. We didn't have to compute it, did we? It fell right there on the line. Before when we looked at this, in particular looking at the empirical rule, we could really only do it if it fell right on one of these. But now with Z-score, we're going to be able to do it for any of them. We'll be able to find those percentages, and I'll show you that in a later lesson. Okay, so that's a negative. That's 2 standard deviations below the mean. That's what the negative means. And one more, 98.2. Now we should be able to do this without even computing it. And I'll just see right here. Without even using the formula, what's it going to be? 98.2 is right here. How many standard deviations from the mean is 98.2? It's 0. If I had to crunch this out, 98.2 minus 98.2 all over 0.62, what's the numerator get? 98.2 minus 98.2 is 0. 0 over anything is 0. So we get a Z of 0 here. Not surprising. So quartiles divide the distribution into 4 groups, and we call these quartiles Q1, Q2, Q3. And you may have seen these. I know you've seen these pop up when we have done descriptive statistics. When finding the mean and standard deviation, they came up on the TI, they've come up in StatCrunch, they've come up in Minitab. So they usually come up by default, because we oftentimes want to know this. So Q1 separates the bottom 25%. Q2 is really the median. Okay, so Q2 is our median. Q3 separates the top 75%. So a graph of this would be like this. So Q2 is the median, right? Separates 50%. Q1 is right here. So the bottom 25% of the value and the top 75%. And here's Q3. So find Q1, the median, and Q3 for the following data. Okay, so you put the data in L1, go to one variable statistic, just like you were going to find the mean. I assume you can do that. And what spits out, which we've kind of ignored, we've looked at the median, but here it is. When you scroll down a little bit, you'll see that Q1 is 67, median's 86, and Q3 is 90. Now quartiles really are just specific percentiles, right? So when we want to look at a percentile, the percentile just separates the data into 2 pieces, right? So when we looked at 25th percentile, which was Q1, it separated the bottom 25%. Same with the median and same with Q3. So suppose we receive a test score back from the SAT. It says you were at the 85th percentile. What does that mean? Does that mean you got 85% of the questions correct? No. It means that 85% of the people who took the test scored below you, or you're in the top 15% of all the scores. That's what that percentile means. And so when you've taken these standardized tests, more than likely it spits back a value. When you get your results back, you may not even get a raw score. It oftentimes will just give you a percentile. Okay, the interquartile range involves the quartiles. So a lot of people think that the interquartile range is really gives you a better visual of the data, a better sense of the data. And all it is Q3 minus Q1. And so an example above that we just did, to find the interquartile range, we just do 90 minus 67, we get 23. So the interquartile range is 23. Rather than the range, because the range, you got to worry about outliers. Interquartile range removes outliers. It's kind of like when you Maybe on some Olympic competitions, they throw out the high and the low. This is a kind of a variation of that, right? Last thing we'll look at is outliers. To determine if our data has outliers, there are a lot of different methods. This is the one this text uses. We compute what are called the upper and lower fences. And if the data is outside of these fences, it's called an outlier. So the lower fence is, everything is 1.5 times the IQR. So the lower fence is Q1 minus 1.5 times the IQR. Upper fence is Q3 plus 1.5 times the IQR. Let's look at an example. So determine if there are any outliers in our body temperature data set below. So we've already looked at this several times. We crunch out this, but we had the same printout before, except that we just kind of glossed over the Q1 and Q3, right? Before, we've looked at median, we've looked at standard deviation, and we've looked at mean, I believe. So now what we're going to do is look at Q1 and Q3 and determine if there are any outliers. So we first have to compute the interquartile range. So the interquartile range here is 98.7 Q3 minus Q1, which is 97.8, and we get 0.9. So now we need to determine our fences. So the lower fence, Q1 minus 1.5 times IQR. So just crunch that out. So here's our lower fence, 96.45. See if you can compute the upper fence. Go ahead and pause it. It's worth it to try to get ahead, try to do a couple of these on your own. Upper fence, Q3 plus 1.5 IQR. And we get 100.05. So we go back to our data and we look to see, are there any values that are below the lower fence and above the upper fence? And there are, right? There's our one that's above the upper fence, 100.8. I don't think there are any others. And here's one here that's below the lower fence, or right on the lower fence, 96.4. And here's where these values show up on our histogram. So this one's an obvious outlier, kind of sticks by itself. This one, again, kind of on the border, right? It actually fell right on that fence. And there's not a hard and fast rule on that. This text would not consider this first one here an outlier, an official outlier, but it's just definitely worth looking at to see if, make sure that these outliers were input incorrectly. Sometimes outliers are merely just mistakes, people putting data in incorrectly. Sometimes people will remove the outliers from the data set because something strange. Maybe this person was actually sick and they thought they were healthy, etc., etc. So if you ever do that, it's best to report both of the values of the, either if you're reporting the mean or reporting standard deviation or some other statistic, to go ahead and report with the outlier and without, so people can make their own judgment on that.